Okay, good morning and welcome back. Today in lecture ML lecture 15, we are going to learn a very important model known as Logistic Regression Model. We had already linear regression, right? So why again another model? Because logistic regression is exclusively made for solving classification problems. Okay, because in machine learning we have already studied if you have data, then how to find the train of the data or how to explore the pattern in the data. That can be done using linear regression model. But other problems which we have are known as classification problem. Say we have houses and we would like to classify into two. One is people's houses, the houses of small size, and luxury houses, houses of very big size, or maybe car, people's car, that means car of small size, and luxury car. So these small, large, for illustrative example, we are defining it. Or maybe, for example, you are getting mail, and mail could be spam or ham, that is not spam, depending on the characteristic feature of the mail. Okay. Then suppose some online transaction is going on, the transaction is fraudulent, it could be yes or no. Okay. Or maybe again somebody has a tumor. Okay, depending on the size of the tumor, the feature is we are for example we are assuming that size of the feature, if it is big, then suppose it could be malignant or cancerous. If it is small, then it could be benign, that harmless tumor. Okay, so all these kinds of problem arise in our daily life. Specifically, that means what we are trying to tell you, that in case of our earlier examples, we are having data and we had a plot like this is y and this is xi, okay, samples, and for every xi the assumption was for every xi we can say this is our hypothesis. So our assumption, fundamental assumption was for every xi there is an yi. For every xi there is an yi. Okay. So that was the case there. So y was a continuous function, although these are all, in machine learning we do some kind of assumption. They were actually discrete. For example, housing price example, right? If I have a house of 800 square feet and corresponding to that we have some price, then 801 square feet, definitely you may not find a price which is different from that. Okay, in that case, in that sense it is also discrete. But if you see globally in a macro level, we assume that for every xi we have a yi. So it was continuous in nature. Okay, in earlier example. But here, as you can see, it is discrete. Okay, discrete in the sense that whatever, say for example, I have a size of house. Okay, and based on the size, I have only two class. Y will not be continuous. Y will be only here 0 or 1. 0 for, say, for people's car and 1 for luxury car. Then giving an email, only thing you can have spam or not spam, right? So that means not spam 1 if you call it, and then spam is 0, or vice versa. We can define all those things. like that. So y is discrete in nature, okay, and specifically the example which so far we have given is an example of binary classification problem. Binary classification, as the term is telling you, that whatever the value of xi, yi will be only having two values, 0 or 1, okay. So this is binary class, only two classes, okay, and all x's has to be classified either in these two classes. And of course, logistic regression is predominantly a binary classifier, but that doesn't mean that it cannot classify a multi-class problem. What is a multi-class problem? Multiple classification problem. Example I can give you, say a student's grading system, right? So we have grade like F is a fail grade, then D pass grade, C better pass, B good, okay, B plus, A plus, A plus is excellent, good, very good, good, fair, pass, fail. So these are the classes, okay. So whatever students marks will be there, okay, there are some, y will take some discrete value. For example, for A plus 80, 90, say the marks 90 and above, 90 plus, okay, A plus. So 80 to 90 A, 70 to 80 B plus, 60 to 70. So with this interval, y is discrete in nature, okay, like that, okay. So this is an example of multi-class problem, and if still we want to use a binary classifier for classifying multiple classes, then how to do that? Say, when I will classify, I will first classify, say, A plus. What the students A plus? Okay, so A plus and rest. So forcibly, so this is one way. Of course, there are other ways we will discuss later on. One way of converting a multi-class problem into a binary class problem. For example, extraordinary student A plus and non-A plus, and within non-A plus all this category will be there. So like similarly A and non-A, that is I will, in the interval of 80 to 90, whoever will be classified as A, all others will be non-A, okay. So similarly fail means fail and pass. This is the two, all others A plus A, B plus B, all others are pass. So that is possible, and logistic regression is a model precisely which can, given data set, which can do this task. Now let us try to understand, okay, why logistic regression. We have spent so much of time and effort in learning linear regression, and why can't we use same linear regression model for together with studying the trend of the data? I decide I will also use it as a classifier, okay. So let us see. Forcibly I am interested in linear regression model. So say I have data, again classes of house. Say if these sizes of house are there, okay, this is people's house, and this sizes house are luxury house, okay, or people's car, luxury car. So these are all means depending on size. I have, just for illustration, I have selected only one feature, which is size, and I am trying to illustrate you, right. So what I have done, okay, fine, I have a regression line. Say this is my regression, okay, regression line HWX, okay, which may be equal to W transpose X. W is the parameter, as you know. And I have, since I have data, say I have fit this line. So this is my regression line, which will classify the data. Okay. Now one problem here is this size of the house, both upper size and the lower size are unbounded in one direction. You see, if I just try to figure out giving a threshold that I will use the same regression line, and I have giving, suppose I have two class now, y equal to 0, that is people's house, y equal to 1, luxury house, okay, and in between I have made some threshold. Okay, threshold is very, very important, always engineers they do, but you will have to be careful. So by thresholding, common sense, 0.5, okay, is a demarcation point beyond which, say, so this is my threshold, okay, this is my threshold, okay, this is 0.5. So in this direction all houses are luxury houses, in this direction all houses are people's houses. Now since, say, there is no guarantee that regression line will be like this, since the feature size of the house is unbounded in this direction, that means this is also luxury house, this is also luxury house, this is also luxury house, and this is also a luxury house, right? Because this is also big compared with reference to our threshold, it is also big. So if instead of collecting this data, say person 1 has collected this data and has fit a regression line, person 2 has collected some outlier like many such big houses, these are also big houses, and his regression line will now be like this, isn't it? So second regression line he has made, and what is happening now? Again 0.5 is the threshold, and this point here has shifted. So this is threshold value, okay, and you see what has happened. What has happened is the following: by merely that person 2 has not done any mistake, okay. This is because these data are also big floors with houses with big floor area, so they are luxury houses, okay. But merely by selecting these data, not this data, which is a little far from threshold value, if somebody select that and make a regression analysis, then his line will be like this, and the threshold, you see, is now shifted here, and now what it will predict? It will predict all these houses of these size houses as people's house, okay, where earlier these houses were classified as luxury houses, okay. So person 2 has not done any mistake, he has followed all the steps and made the regression analysis, and still he could not classify wrongly classified houses. Person 3 also similarly could also, since you see this is also unbounded, the lower sizes, small sizes are also unbounded in this direction. So if somebody has taken lower size houses, floor area houses, which are far from the threshold, okay, and try to regress, then his regression line could be like this, okay. And then what is happening? You can see by virtue of this this is shifted here, okay, and what are those houses? Now it will classify as luxury houses, but are these houses are luxury houses? No, they are people's houses. By simply shifting this regression line, it again misclassified. It failed to classify correctly. So linear regression model as a classifier is a flop, okay? No, it is not possible, okay? So that makes our quest for finding an alternative. Okay, what if somehow we could separate these two classes, okay, in two extreme directions using a function which has two asymptotes, and each for each class, then perhaps the problem could have been solved. Okay, let us see what I am trying to tell you, whether it makes sense or not. So this is called logistic regression. We are trying to modify our hypothesis. You see, this is our hypothesis or predictor, whatever you can call. Predictor for linear regression was W transpose X. W was the parameter, X0, W0, X0 plus W1, X1 plus Wn, Xn, like that. It was for linear regression. Now for logistic regression, what we did, we modified the hypothesis by putting W transpose G as a function. G of this is a function, okay, is a function G. Now suppose this is Z, so this is actually hypothesis is equal to a function Gz, where Z is a real number, such that, what is that function? Function is 1 by 1 plus e to the power minus z. Okay, and this is incidentally is known as sigmoid function or logistic function. Okay, if you plot this function, okay, z and gz, okay, gz versus z, if you plot, then what you will see, you will get two asymptotes passing through the threshold. Say now I have this one class 0, this is 1, and one class will be always represented by this asymptote, and another class will be represented by another asymptote here. So as if the samples has been clearly separated by this sigmoid function. Now let us see what we have achieved. Intuitively what we have achieved is very clear. Now two asymptotes are actually representing two classes. So there is no chance whatsoever of misclassification. Okay. Say we have a data set. We need to find the model parameter W. So suppose that we have not discussed here, we will slowly discuss that. Somehow we will be able to find the parameter W. Then our hypothesis Hx parameters by W equals to 1 by 1 plus e to the power minus W transpose X. This is actually the structure of our new hypothesis. It is not simple W transpose X, but it is kept within the logistic function. Okay, and this now I am able to make a decision by calculating the probability. So this will be able to, the hypothesis Hwx actually will be able to calculate what is the probability that a given sample X belong to a class 1 parameters by W. Okay, so this is again we know that maximum likelihood of W. From there we can find out W also. Okay, that what is the maximum likelihood of W, show that probability for a given sample X belonging to a class y equal to 1 is maximum. Okay, and there are other ways also for determining W, we will discuss. But basically what it is doing, it is calculating the probability. Now you see here, okay, say for any, so for here, any data set here, so probability will be belonging to a class 1 will be 1, and slowly the probability will decrease when it is so belonging to the class 1 will decrease, it will be crossing this, and probability will decrease that it will belong to a class 1. Okay. So similarly, for class 0, the probability, the sample, as soon as the sample comes in this zone, the probability that it is 0, belongs to 0 class, will be diminished significantly. Okay. So since it is calculating probability and we have a binary classification problem, then definitely probability for a given sample x, the probability the samples belongs to a class y equal to 0 parameterized by w plus giving the sample x, probability that the sample belongs to a class y equal to 1 parameterized by w must be equals to 1. Okay. So from that you can calculate, once I calculate the this probability, okay, this probability can also be calculated. It is as simple as this. Say in data, the probability of a given sample belonging to here, it is here, is 0.7. Then what is where is the so 70% chance that it belongs to a class 1, but where is the other 30%? So 30% is a chance that it also belongs to class 0. Okay. So this is the logistic regression's heart is the logistic function, which has been designed like this, and that can solve the problem. Okay. Wait a minute, that can solve the problem provided we can figure out a way to calculate W. Okay, and for that what you need? You need a cost function. If you have a cost function, now again the question is the same cost function which we used, beautiful cost function which we used for linear regression, okay, 1 by 2m, all of you now know, okay, 1 to m. That was our beautiful cost function for linear regression model. Question is, can you use the same cost function, least square cost function here and still get the beautiful nature of the cost function over W? The answer is no, because this has changed in this form, okay, and e to the power something is a series, okay. So even if you try to just put these values, this value this, then the nature of the function will not be convex, so it will be something like very bad, okay, full of local optima, okay. So you understand why? Because the very nature of the changes which you have made, your cost function could be like this, which is not acceptable. Why not? Because there is no more a global optimum point, okay. Then if it is not there, then the beauty of finding W by running optimizer, that is the gradient descent algorithm, on this cost function is gone. What to do? In the next class, we will try to find intuitively a intuitively first intuitively the nature of the cost function for logistic regression. Okay, so that's it for today, and we have introduced you that what is classification problem. Okay, when y is discrete for some x, then it's a classification problem. Binary classification problem is very popular, and we are trying to develop a model which is known as logistic regression model, which can classify our data into two classes. And henceforth, I think rest of our course will be dedicating for solving the classification problem. Okay, so this is one model for solving classification problem. Slowly but steadily, we'll study many models which can classify your data. Okay. Till then, stay safe and bye bye.